Okay, good afternoon and welcome to the first talk in the SLDS webinar series in 2023. And today we are honored to have Dr. George Michailidis as our guest speaker. And by the way, George is the chair-elect of the SLDS session. George is a very prolific researcher, and his research interests are in high-dimensional statistics, change point analysis, large-scale networks, machine learning, stochastic control, and their applications to biomedical, engineering, and financial data. He is a fellow of ASA, IMS and ISI. Besides the chair-elect of the SLDS section, George has done a lot to the statistical profession. He was like the founding director of the Informatics Institute at University of Florida, and he served as editor-in-chief for Electronic Journal of Statistics and AE for many statistical journals, including JASA, JCGS, Technometrics, and Nonparametric Statistics. And today, George is going to talk about a statistical model for mixed frequency data and their applications. Welcome, George.
Thanks much, Sophia, for the kind invitation and the introduction, and thanks everybody for attending. So one of the reasons that I chose today is the following. So today, the GDP forecast came out, the preliminary estimate, and essentially, I have this screen capture from the Yahoo Finance site, and that says it beat forecast to cap a resilient 2022 year and so forth. However, if we go back about 6 months, the headlines were very, very different. So the past summer headlines were that there was a lot of discussion for recession because the corresponding numbers seem to be shrinking and therefore pointing out to a contraction of the economic activity. And for those of you that have following other economic news, especially for 2021, late 2021 and the whole 2022 and ongoing right now, is the discussion about what is the inflation rate, and because all these have a lot of implications. So since today it was the announcement or the preliminary estimate of the gross domestic product, and a good chunk of the talk is going to focus on how we can build statistical models to forecast this core macroeconomic indicator, and I'll explain why this is important and what are the challenges and why some of the statistical models that leverage mixed frequency data, many of you may not have seen or heard the term, is important. So the gross domestic product, a little bit of introduction or background, is a comprehensive measure of economic activity, and essentially it measures the value of the final goods and services produced in a country's economy. And it's a complicated measure, and the key thing is not the absolute level, but what is important to a lot of stakeholders is changes from quarter to quarter, because this is a variable or an indicator that is measured on a quarterly basis. And it's well agreed that it's the most popular indicator, and it has a lot of implications for many stakeholders. Definitely impacts consumer sentiment. That's why I showed you some of the headlines from past summer. Definitely, it has indirectly an impact on short and long-term household and businesses' investment decisions, and also on financial markets. So you may say, okay, but on the other hand, we have these measurements. You just showed us a headline that there was an estimate of the change from quarter to quarter, or you can also annualize it. So why is this a challenging problem? Well, here are a little bit of further background. So these GDP estimates are derived from essentially the national income and product accounts, but use a lot of data sources. Many of them come, of course, from federal agencies that are tasked to measure these components that constitute the GDP. So federal agencies that belong to the Commerce Department, the Labor Department, the Agriculture and Treasury Departments. And also they are supplemented by data from additional sources, private sources, international organizations, businesses, and trade associations. Because the GDP, as the previous slide shows, is both goods and services, and therefore there are a whole bunch of components that come into calculating the final number, and then of course calculate the rate of growth from quarter to quarter or from year to year. And the agency in the US that is responsible for calculating these numbers and consolidating all this information from all these other agencies is the Bureau of Economic Analysis in the Commerce Department, and publishes the number on a quarterly basis. So today it was the publication day for the last quarter, the fourth quarter of the previous year, of Q4 of 2022. However, as we're going to see on the next slide, the number, both the absolute number in trillions of dollars, what is the gross domestic product, and also the rate of change that is much more important for most of the stakeholders, whether the economy is growing and at what rate is growing, or it's contracting and at what rate is contracting, is not the final number. As the last bullet point shows, is a number of revisions occur both in the short run and over a 3-year period. So you may start wondering, okay, this is a very important number. Why is this happening? Before I discuss that point, here I plotted from, for those of you that have worked with macroeconomic data, or in general other economic data, this is the FRED database that is maintained by the Federal Reserve Board of St. Louis, the Federal Reserve Bank of St. Louis, and it's a wonderful resource, very easy to use, and has all sorts of data at different granularities. So if you're interested in working with similar data to illustrate statistical models, this is a wonderful resource. And as you can see, essentially starting in 1950, of course, you need sort of to use some deflator in order to control for inflation in prices. So this is the real gross domestic product adjusted for inflation. And, I extracted the data from 1948, past the Second World War, until the last quarter of 2020, the third quarter of 2022, because the number for December just came out. And of course, you see an increasing trend, and the bands in gray, essentially, the software allows you to superimpose periods of time where the National Bureau of Economic Research has declared that the US economy was in a recession. And as you can see, there's always a dip around to those periods. Some of them are very mild, and many of you may recognize the very significant dip around the financial crisis. And obviously there is another huge dip, temporary dip, because of COVID in the second quarter of 2020. On the other hand, obviously, this is not the most interesting measure to look at. And usually, as I mentioned, the key variable that you would like to model is the rate of growth. So changes quarter over quarter. And that will be the topic of our statistical models. Okay, coming back to why the number that was published today is not the final number, and it's not going to be the final number for quite some time. Let's look at what is the release schedule. And this starts introducing a number of challenges that these mixed frequency data are trying to address. And of course, then they create other challenges of how we can incorporate mixed frequency data in a regression model or in a multivariate time series model. So today what we had was the advanced estimate, or the first estimate, which comes 1 month after the end of the corresponding quarter. So we are at the end of January 2023. So we saw the advanced estimate of the GDP for the last quarter, Q4 of 2022. At the end of February, there is going to be the second revision released by the Bureau of Economic Analysis. At the end of March, there's going to be the third revision. And then there is a schedule, what they're called the latest revisions. There is a schedule that do additional revisions at an annual and 3-year updates. So essentially sometime in July of 2024, so we're looking really almost 18 months from now, there are going to be another update of the number of the advanced estimate that came today, and there are going to be additional updates up to 2026. In some cases, especially after the first annual update, it turns out that this is sort of the final number, but essentially in periods of very high volatility, where the data sources are very noisy, there are continuous updates even 3 years down the road. So, so essentially, I have already pretty much discussed the schedule, and I just gave you an example for the fourth quarter. Here I'm giving another example, but you see how many additional revisions are gonna come. So on the other hand, you may say, okay, from a modeling perspective, which revisions matter? And also, this is for a modeling perspective, and also for the stakeholders, which numbers matter. So the advanced estimate is the most consequential for stakeholders because it gives the first glimpse, the first look at where the economy was at the end of 2022, at the previous quarter. So, because up to that point, you have no clue, you only have the numbers for the third quarter, so they start becoming kind of stale. So right now, this is the most consequential one. And the second one that, the second and the third ones that come at the end of February and at the end of March, as I mentioned, are also fairly consequential because in many cases, the advanced estimate is very noisy and actually fairly inaccurate, and we'll see why. While the historical revisions are of interest for retrospective analysis, so when people try to understand and finalize what was the depth of the recession that occurred during the financial crisis of 2008, how much did the economy contract? So at that point, you would like really to have nailed that number because then you're trying sort of to extract insights of what were the forces that led to it, how big was the contraction, and so forth. Or in other periods of rapid economic expansion, like the late 90s, how fast the economy was growing, and again, trying to get insights. So essentially, in many cases, and I'm going to show you some examples, the number that came out today is maybe fairly inaccurate. At the same time, a lot of stakeholders would like sort of to start making decisions, and obviously start making decisions on a number that's going to turn out to be off, not by a tiny percentage, but it may be off by a significant margin, is not sort of ideal. So over the last 15 years, people have started thinking, as other data sources have become available, how to utilize other sources and include them in statistical / econometric models. A lot of the work has come out of the econometrics literature in modeling, so that essentially you can provide better forecasts that are potentially much more accurate than at least the first official number. You know, eventually, you know, after all these revisions, the number becomes the number because all these data sources report much more complete numbers. The problem is that the GDP is comprised of all these components, and all these components are derived from surveys, and that's why right now a lot of the response rate for a number of surveys that go into calculating the final number are not really finalized. So many of them have estimates, so they have errors. That's why, there are these inaccuracies. It's not that the methodology is not correct, but there are all these technical issues that in order to collect the data, clean the data, curate the data, check the data, takes more time, plus sometimes the response rate is low at this point in time. It's going to improve by February and so on and so forth. However, there are a lot of other indicators, but even if they have a little bit of a publishing delay, they're available on a monthly or even higher frequency. So, and here I give a whole bunch of examples: interest rates, money supply, industrial production, a lot of private surveys these days on unemployment, market sentiment, and essentially based on both macroeconomic theory and statistical modeling, you can start thinking of how you can leverage data that are published at a track important indicators at a different frequency. So you have data for every month, so you get these updates, how you can sort of leverage them in order to predict a low frequency variable that is only available at the quarterly frequency. So you can see where, from a technical perspective, the challenges starts coming about. You have a lot of variables that you have monthly data, and then you're trying sort of to create models that both regression models, where it's going to be the focus of the first part of the talk, and I'm going to go into more detail, for a quarterly variable. The problem becomes compounded when you would like maybe to use a multivariate time series model, and then suddenly you realize that your data are not appropriately aligned. You have the monthly data, you have the quarterly data, and there is this misalignment in terms of the frequencies. So you don't really have the observations the way we really want in order to develop and test a model of interest. So essentially that's sort of the challenge. And there are two aspects. One is, let's say that we had all the data by now. So we have complete data up to December 2022, and therefore we can try to forecast what will be the estimate of the rate of change for the GDP for the first quarter of 2023, so for March 2023. But at the end of January, or let's say that right now you are at the beginning of February, you have already, for the monthly variables, you have already measurements for January. So how can you start leveraging that advanced information in order, again, to do a forecast for March? And the same when you acquire the February data. And even at the end of March, when you acquire monthly data at the end of March that come with no publishing delays, whereas the monthly measurement, the quarterly measurement for GDP is not going to be available until April. So you see, even at the end of March, you would like possibly to be able to have a better forecast. So this is sort of the statistical task, and you can think of the same holds for a lot of other variables that maybe are at a monthly cadence, and the data are available at a weekly frequency or daily frequency and so forth. And here I'm going to talk a lot about some of these models. And here I'm just illustrating of the forecasting. And the point here of this plot is that the estimates by using this methodology of mixed frequency was fairly close to the final actual measurement that became available years after the quarter of interest. Okay. So that was sort of the introduction. Let's start turning a little bit our focus to the statistical modeling. And initially, I'm going to focus on the regression model because it's much easier to illustrate the ideas. And then I'll have a few slides, what happens, what are the challenges for multivariate time series type of models. So as I've already mentioned, is you're trying to build a model where your data are sampled at different frequencies. So somehow you need to rearrange them and so forth. For a regression model, things are a little bit simpler. So we have a response variable, which is a low frequency variable. Let's say that is at a quarterly frequency. And I only have, to make things simple, a variable that I measure at a higher frequency, monthly frequency. So let YT be the gross national or the gross domestic product, and at a monthly frequency is the interest rates. So essentially, what I would like to do is, like in any regression model, a lot of these macroeconomic indicators have strong memory or relatively strong temporal dependence. So obviously, I would like first to leverage the temporal dynamics of the variable of interest, which is at a quarterly level. So that's why essentially I regress it on past lags. And of course, there is an issue how I do lag selection. And there is a whole bunch of very mature techniques of how to do that, use information criteria and so forth. And then here I have essentially the monthly variable. So essentially in this particular case, my design metrics is gonna have 3 variables. So I need to expand, although I have a single monthly variable, essentially I'm gonna, and if I only had 1 lag, so here things get a bit more complicated because I want maybe to have a lot of lags. So if you only isolate this part of the picture, essentially we're gonna have 3 variables from the previous quarter. We have our response variable for this quarter, and maybe we want also to regress it on the previous quarter. And essentially, I'm gonna have these 4 coefficients that I need to estimate. Obviously, given the fact that these higher frequency variables are also exhibit fairly strong temporal dependencies, and therefore past lags may still be informative for better forecasting, I may have many, many more lags. So you see where the challenges come from. This component is fairly straightforward. You know, we have been doing this type of distributed lag regression models for a very long time. They have a very mature theory, and things are fairly straightforward, both conceptually and technically. However, here, although we had a single variable, we need to expand it on a monthly cadence. So essentially, you're going to have the latest month in the quarter. So as I have a lot of quarters, these are my samples, the latest month in the quarter, let's say December, September, June, March, is going to be the data for one of the variables. So one of the variables corresponds to the last month of the quarter. The other variable in my design metrics corresponds to the middle month of the quarter, and the third one to the first month of the quarter. If I had weekly data in a quarter, roughly there are 12 weeks, so then you're going to expand that weekly variable into 12 new variables, and then you're going to create your samples appropriately. But as you can see, you start having a lot of regression coefficients because you also would like to incorporate not only the data from the last quarter, but from previous quarters, because you believe that these are maybe helpful. So you have a proliferation of regression coefficients, and many of you may have started thinking, okay, that's not a very big deal because these days we know how to handle high dimension regression. So although you have a lot of beta J's, we have a lot of techniques. So here is the upshot. The number of parameters to be estimated can be very large. And it's because here I'm only showing you for one variable. But if you have a lot of variables, and then you need to expand them the way I presented for a single variable, and then regress them on the previous lags, you have a proliferation of regression coefficients very, very fast. So your parameter space starts growing pretty fast. So you can have hundreds of indicators, and there has been literature and applied papers that use hundreds of indicators in order to do this forecasting. And at the same time, the frequency, the higher the frequency, the more new variables you have to create. So you may end up with a very large parameter space. Yes, I'll send the PowerPoint to Sophia so she can distribute it through the usual channels. And there are the main lags for each indicator. So there is a need to reduce the effective number of parameters. And the other thing, as I've already mentioned, several predictors are lags of the same indicator. So you may be tempted just to use some straightforward frequentist or Bayesian technique to select the most important variables. You can think of Lasso type of regression or Bayesian variants of Lasso type of regression, and then essentially the technology is there. Before I go there, the econometricians had an interesting idea, and it's gonna sort of be utilized or leveraged in our framework later on. So essentially they said, given the fact that one of these indicators has all these lags, I don't want the parameters of the lags to be completely free, but I would like sort of to parameterize them. And for example, you can use a nonlinear function. And there have been a number of proposals in the literature of this type of functions. So what we see here is, as we had one of the variables, once we did the expansion of the monthly variable into 3 variables in order sort of to align the data, you may say that the regression coefficients may be as a function of a singular coefficients times the parameters of this polynomial. And you can hear what I have plotted is, depending on the number of lags and how you pick the theta 1, theta 2, theta 3s, essentially you can give different shapes of this function. So essentially, in this particular case, you can start imposing structure. And for example, of course, the thetas need to be estimated from the data. And this polynomial is fairly flexible because essentially the magnitude of the regressions across lags can go down very, very fast, or it may go down at a slow rate, or it may be roughly constant for a certain number of lags and then smoothly and gracefully decay, or for some previous lags, it may be higher magnitude and then decay, and so on and so forth. So this is a very flexible way. And remember that the way they parameterize this, that for all variables, you can sort of impose constraints and use the same thetas, or for different values, you can use same thetas. But in general, this is a parametric way of decreasing the number of parameters. So the estimation, of course, needs to be by nonlinear least squares because you have nonlinearities. And this is known as the Midas technology, mixed data sampling framework, introduced in the Journal of Econometrics. And it has definitely flourished with a lot of application papers. And it's available in R. There is a Midas R package, if anybody's interested in trying it, and so forth. So there is another question, are all of the indicators usually continuous? The majority, yes. You can think of interest rate, money supply. There is some interesting new work where people have made available to the community indicators that capture news events, some big announcements. So in that particular case, some of these indicators that capture events are of a categorical nature, but most of the macroeconomic indicators are numerical variables. Of course, you need sort of to maybe go through a number of transformations because, as I showed you, the data are not stationary, but the actual measurements are numerical. The majority of them are numerical in nature. Thanks for the question. So coming back to the MIDAS, okay, nonlinear least squares, there are good algorithms out there. So estimation is not a big challenge. And but the key challenge is that you impose the lag structure directly, and it can be fairly restrictive. And the selection of lags can be expensive because at some point you need to start invoking some information criteria. But the key thing is that you're not flexible enough. So thinking about this problem, another approach is just leverage the technology that is available these days on sparse regression. However, that's not going to work well, and I'm going to show you an example in a second, because you have, through all these indicators and this expansion of the high-frequency variables, a lot of correlations between your predictors, and at the same time, you still believe that there is a structure on the regression coefficients over the lags. So, for example, you would like to, in a lot of applications also it's not only a forecasting exercise, but you also try to impose some interpretability. You would like to select a small number of adjacent lag coefficients. What you don't want is select the first lag, from December, and then jump and select December of the previous year. What happened to all the intermediate other lags? That can happen, depends on the structure of the data, but then you start sort of worrying of whether your model is capturing some spurious correlations, and it's much more difficult sort of to present it to stakeholders and defend such a model. So what we would like is to essentially focus on a small number of adjacency lag coefficients. In many cases, we would like sort of the shape of the coefficients to have a decaying pattern. Fast or slow, the data need to decide that. But we don't want a sawtooth pattern that, in some applications, without some restrictions, this shows up. And essentially, we're trying sort of to decrease the effective dimension of the parameter space by appropriate variable selection. And in this case, we are going to use a Bayesian approach. So right now, slowly, I have started getting to the technicalities. So let me illustrate our idea, and we call it the Bayesian nested lasso because it shares similarities with a frequentist version that was introduced in this paper in the context of high-dimensional covariance estimation. But here we borrowed the idea and we modified it, and we're going to use it in a regression setting. So here I have, think of one of my variables, and I have L lags, as the indication shows. And essentially, I'm going to reparameterize them in this particular way. So for the lead indicator, so for the leading lag, I call it theta 0. And then essentially, I have this multiplicative representation. So I take products of my thetas. And what you can see is that these requirements are going to be automatically satisfied because once the data select a theta k to be 0, all the beta j's, let's say that here you select theta 2 to be 0, from beta 2 all the way to beta L, all these coefficients are automatically 0. So on the other hand, we have kept the first two adjacent leading lags, and then everything else has been set to 0, and so forth. So it has this very nice property, and at the same time, it can impose those type of decaying patterns, and we're going to do something more in the sequel. So that's a very straightforward idea, and therefore the question is, right now, this is our new parameters that have this nice structure, and the question is, in a Bayesian framework, what priors we need to impose, and so on and so forth. But before I go there, why did we start thinking about this framework as opposed to just using on the original beta coefficients a standard Bayesian sparsifying prior distribution like spike and slab, the prior that has been used in high dimensional regression to select a small number of variables. So here is a simulated example. I have a single predictor, and there are 4 true lags, and these were the coefficients. And we used this parameterization that I described on the previous slide, and also a vanilla spike and slab prior distribution. Okay. So in the first approach, I haven't told you exactly how we impose the spike and slab prior distribution on the theta j's. That comes up in the next slide. But the second approach is standard spike and slab prior distribution on the beta j's. So since we didn't know the true lag, although we generated the data, we assumed a model with 20 lags so that it has a large parameter space, and we had enough adequate signal and adequate sample size. And it turned out that from the proposed approach that I'm going to describe in the next few slides, essentially it picked the 4 true lags and then set all the other coefficients to 0 through the thetas, and therefore then you can start translate them to betas. On the other hand, the standard spike and slab estimates 15 lags. And of course, the estimation error is much higher. But the big problem is that essentially it's misspecified completely the lag structure. And this was kind of a toy example with a single predictor. When you have hundreds of predictors and then you need also to do this expansion of the variables, you start getting very weird patterns. So let me build the full model and introduce especially the spike and slab distribution on the thetas and some additional twists. We have already seen the model, and the only difference from the previous slide is that right now I assume that I have k predictors because that's what I want to have in applications, and the rest for every predictor, I can accommodate different frequencies. So that the PJ is that all the variables don't need to be on a monthly frequency. You can have other predictors that are on a weekly and so forth. So essentially, I can write it as in a compact form with the appropriate alignment of the data that I briefly explained in a simpler example. So essentially, you have a nice regression model where P right now is the D lags that come from your low frequency predictor. And then essentially, all the summation of all these other variables based on their lags and the number that we have k variables. And I have already shown you the reparameterization and with the property that we want. The nice thing is that an unstructured sparsity in the thetas, that's the key observation here, will induce a sparsity cutoff, as I explained, with, for example, if theta 2 turns out to be 0 in the betas, and therefore facilitate lag selection and reduce the effective number of variables that enter the model. And this is sort of the core message. The rest is technicalities of how exactly we're going to put prior distributions of thetas, but essentially you see where this is going because any unstructured sparsity in the thetas will do sort of the job. So what we select is we're going to use spike and slab prior distributions, given the fact that we don't have any constraints on the thetas. And essentially, if we introduce these latent variables, the gamma j's, where the appropriate for the ith variable and the jth lag is active or not, then there is one multivariate normal distribution. And if it's inactive, so it's not going to be selected, there is another multivariate distribution. So it's a slight modification of the standard spike and slab because we allow some variability even when the variable is inactive. And here you can see that the spike variance, when the variable is inactive, is chosen to be much smaller than the slab variance. So instead of putting a delta function here, which can also happen if you set the spike variance to 0, the tau 0, we allow a little bit more flexibility. We found out that this works well in practice and doesn't really impose any significant. It's a little bit more flexible. And then probability Q, the variable is active, and 1 minus Q, the variable is not active. And as standard in a Bayesian framework, the error variance is given by an inverse gamma with a certain shape and rate parameter. And then, of course, for the autoregressive coefficients, we just use a normal prior distribution. These are completely unrestricted and so forth. So without belaboring the technicalities, the nice thing is that you can come up with a nice algorithm because all conditional posterior distributions, the way we have set up the problems, have nice closed form expressions, and therefore it's easy to sample from them. Very standard technology. As that's essentially the message of this slide. So essentially, you can have really efficient sampling algorithms, the way we have set up the problem. And here is in somewhat involved notation, the Gibbs sampler and the steps that you need to go. Essentially, you go through all these conditional posterior distributions, through iterations and so forth. Everything's at this point fairly standard. Again, the key point was this: once you have done this parameterization and you realize that, then you can start having a number of ideas of how to complete the model specification. However, we wanted to put one more twist, which was motivated by those lag polynomials that we saw in the Midas methodology. And because up to this point, the methodology that we have doesn't impose any constraint on the magnitudes of the betas. The thetas essentially are completely free. But on the other hand, as I mentioned before, it makes a lot of sense that lags in the further past have much smaller coefficients, and therefore they have smaller influence on the current values of the response variable. That's very, very reasonable. So you would like sort of to allow the model to leverage that intuitive property. And essentially this is the motivation came from the lag polynomials that we saw in the Midas methodology. How are we going to do it? Essentially through the slab variances. So we parameterize the slab variance when the variable is active through a following generalized logistic regression that depends on two parameters, B and C, that control essentially the rate and shape of decay. And you can see right now it's on the slab variance, it's not directly on the betas, but essentially you see similar patterns of what we saw in the polynomials that were used in the Midas methodology for the regression coefficients directly, but that's much more restrictive because then you essentially impose a certain shape, whereas here, this comes, you're trying to put a more informative prior, where these parameters, of course, become hyperparameters that need to be estimated from the data. And we found out that in numerical work, we impose prior distributions uniform on these hyperparameters, and the rest of the framework is the same. Again, of course, the full conditional posteriors of all the parameters again have closed form, apart from those of the hyperparameters C and B that parameterized the slab variance. But since they have bounded range, we can have a simple accept-reject algorithm. So again, these are univariate parameters, a little bit more computational work, but again, very standard technology to be leveraged. I'll skip the theoretical guarantees. You can prove that under this parameterization and then imposing that leads to kind of a nested class, so that's what we call it, and then imposing spike and slab prior distributions and having the addition of the parameterization of the slab variances. Essentially, you can have model selection consistency under fairly standard conditions, but many of you may have seen in a high dimensional regression. I don't want to spend too much time on simulations. Just to illustrate a couple of points, I would like to discuss a little bit more the application and then what happens in the multivariate case. That's much more informative. So we try different simulation settings. So the key question that the simulations try to address is not this model does so well compared to the competitors, but this model is flexible enough, and essentially, even if the data were generated from another mechanism, by just having the model the way we specified it is flexible enough and performs well. So it's a flexible enough model. So we had a number of settings. What we call neutral setting is it doesn't favor the Midas methodology, which is very well established. There are a number of papers, and a lot of people have used it in applications. And it doesn't favor the proposed Bayesian nested Lasso methodology. Then we had another mechanism where the simulation settings favors the Midas methodology. And then we had a third setting that, again, it was favored in a different way, the Midas methodology. Again, these are some technicalities, but the upshot is if the data are generated from a mechanism that is much more aligned with a different methodology of how to set up the regression, essentially by using these parameterizations and nonlinear least squares and so forth, how flexible is the proposed model, especially given the fact that I made such a big deal about lag selection. So before I show you the simulation results, for one simulation setting, you can calculate the posterior densities, so you get the natural uncertainty quantification, so you can really visualize the results, how much uncertainty you have for particular lags and so forth, standard things. And especially the last 2-3 years, as you can see from the references, the Midas methodology, as I mentioned, is well established. And there have been a number of papers for the last 15 years where that group and other groups try to improve it, tweak it, improve algorithms and so forth. But the last 2-3 years, a number of other groups have tried to couple the Midas methodology with ideas from high dimensional regression, like Lasso or Bayesian versions of Lasso with spike and slab. And we wanted also to try those. So in the neutral setting, the proposed approach, given its flexibility, does well compared to the relative estimation error and so on and so forth for different sample sizes. So that's the upshot. Much more interesting is what happens when you use a data-generated mechanism which is particularly favorable to the Midas methodology. And as you can see, obviously, given the fact that simulated data from a Midas model, it better perform well. But our approach is very, very competitive, stays very close for both the two different type of mechanisms. The other thing is, here, we gave the maximum advantage to the competing method because we supplied it both with the correct family, whether it's an almond that has a certain shape or a beta polynomial. Essentially, we provided information whether the shape of the decay is according to this polynomial or according to another polynomial. So you provide much more information to make it as favorable as possible. And also the lag information, how many lags you should consider. the moment you don't specify for the Midas approach all that extra information, given how much main parameters you have and the inflexibility, actually the proposed approach even beats an approach from which the data were generated. So I'm not trying to beat on Midas. It's an established methodology and it has shown some very good results, but I'm trying sort of to show that through the nested lasso penalty and the appropriate specification of the priors, it's a very flexible and very competitive approach. So back to GDP forecasting, we transferred the data to forecast annualized quarterly growth at the annualized rate. We looked at data from January 1980 to 2017. And then we evaluate out of sample forecasting, starting at 2000 and then having a moving window for all this data. So I'm not going to show you COVID results, and I'll explain why in a second. And a lot of the competing models that we tried in simulation, there are some other flavors. So this is our model, Bayesian Midas approach that we saw in the simulation, frequentist Midas approach that we saw in the simulation. We threw a sparse group lasso by trying sort of to group coefficients, and we calibrate everything to a random walk model. So when you see a number less than 1, it means that this is a very naive benchmark. It's completely univariate. It doesn't use any of the other high frequency indicators. So this is a very, very naive benchmark. So hopefully most of these approaches should beat it. So if you see in the next table a number less than 1, these approaches are doing better in terms of forecasting performance. If you see a number larger than 1, it means that these approaches cannot even beat a very naive, trivial to implement forecasting model. So the good news is, so here we looked at different horizons. So let me explain the horizons. Here is pure forecasting. So you have the data up to December and you're trying to predict essentially up to the 4th quarter and you're trying to predict March. Here, your low frequency variable has stopped in December, but you have the January update for the monthly variables. Here you have the February update. Here you have the March update. But the quarterly variable is still stuck at the previous quarter. And here you go pure forecasting beyond the next quarter. And again, in an intermediate way. So here, of course, you use up to this, to the March data, and then you need sort of to have a mechanism to forecast those variables and utilize them. So the good news is that all these more sophisticated techniques beat the very naive benchmark, and this is the good news. But again, the upshot is that the proposed method is flexible enough, and these are real data. It's not anything that has to do with simulation where you can always tweak the parameters. And then, of course, we wanted also to examine, actually, this was a good suggestion by the referee, where the superior performance of the proposed method was due to sample uncertainty. So standard Mariano-Dibble-West test was used. And the answer is that apart from some of the large horizons for some of these other methods, the improved forecasting performance was real and not because of sample uncertainty. So to wrap up the first part, and I have a few slides going to the multivariate, we have a little bit more time. So mixed frequency data have a number of applications. Most of them, at least to the best of my knowledge, come in the sphere of these economic indicators. There have been a lot of other applications with commodity prices, with some financial data. They start showing up in other areas where the reason is that some variables are measured by sensors in an environmental sensing setting at a lower frequency and some others at a higher frequency because you have deployed different number of sensors. But to the best of my knowledge, a good chunk of the methodologies of the applications come from economic type of applications. And the key point, the takeaway message is that the structure of the variables, by taking inappropriate consideration and essentially imposing a flexible mechanism for variable selection and lag selection, has its advantages compared to other methods in the literature that impose much more structure that may not be flexible enough. The other advantages is that, of course, you have the natural uncertainty quantification for the inclusion probability, so you can see which variables are important and how many lags. So here is a heat map as a function of lags of a lot of core variables, and you can see that the first lags are much more significant to be included in the model, and essentially beyond lag 6 on the monthly frequency, so half a year ago, essentially, the inclusion probabilities become fairly tiny. And you can see the different variables have different lag selection. Before I switch and I give you a hint of what happens and what are the challenges for multivariate time series models, why do accurate forecasts matter? Okay, from a statistical perspective, it's interesting to build new models, think of how you can incorporate this mixed frequency data. And here I pick an illustrative example, which was at the end of the 1990s fast growth of the US economy. So we focused on the second quarter of 2000. It's easier sort of to read the slide rather than doing it on the plot. So I'm giving you the numbers that were published 1 month after the end of the second quarter, 2 months, 3 months. And these were sort of the numbers, 781, 812, and 818. So you see that the advanced estimate that came out of the Bureau of Economic Analysis on a annualized basis, this is not quarter over quarter, but we annualized it, was a little bit less than 8%. And then 3 months down the road, as more the data were refined, all the surveys that I mentioned, it was a little bit above 8.2. The final estimate after the 3 years of revisions came out at an annualized rate to be over 9.5. So you see there is a huge discrepancy. The first number that you get, of course, it's still an impressive number in terms of annual growth, but it's almost 2% below the final estimate. So for a lot of the stakeholders, this big discrepancy creates very different expectations of how the economy is performing and about their decision plans, households, businesses, the Federal Reserve that sets economic policy through the interest rates, and so on and so forth. However, these models, and for other competing models, by using all these mixed frequency indicators, came very close to the final number. So the upshot is that there was a lot of information baked into the more high frequency indicators that were very accurate to the final number, but was not materialized until 3 years after all the revisions. So, and especially in periods of rapid economic expansion or rapid economic contraction, COVID is an exception because that was a very artificial induced recession because essentially for public health reasons, the big sectors of the economy were shut down and none of these models worked well. I've tried all these models and the contraction of the GDP in the second quarter of 2020, the recorded number is around 20% or 25%, something like that. And these models can go up to 12%, no matter how fancy you are, because, the information took quite some time. I mean, it was an unprecedented contraction. So in the last 5 minutes, I just give you a very high level. Going beyond linear models. So there are 2 directions that the community has started exploring. One is, instead of having these linear regression models, what about more machine learning type of models? You can start thinking of decision tree regression, random forest regression, using kernel regression, or going with neural networks. But there have been previous presentations at this webinar. So, because there might be nonlinearities in the data. And the other is, if you are not interested in forecasting a single economic indicator, let's say GDP, but you are interested in doing a forecast of production and the GDP or interest rates or inflation, you may be interested in multivariate models. This is fairly straightforward because once you do the organization of the data, as I showed you, you can throw any nonlinear model that you are interested in and use random forest regression or kernel regression or a neural network. So it's just a matter of which regression framework you would like to utilize. However, here, there are a number of issues. So I'm going to show you vector autoregressive models. And the reason is that the econometricians and macroeconomists are very fond of vector autoregressive models for a number of reasons. So essentially, it's a multivariate model. You have p-response variables, and essentially you regress past lags. So it's essentially a multivariate time series model. And this AJs, the transition matrices, capture these lead-lag cross autocorrelations. And as I mentioned, it's a workhorse model in microeconomics, and it has found a lot of other recent applications. And however, the moment you have multivariate data, if you were trying to visualize how your data look like, and you expand the data on the monthly frequency, for the low frequency variables that are quarterly, you're going to have missing data. So therefore, one of the approaches is you need to impute at the monthly frequency the missing values for the low frequency variable. So this is a missing data approach, and there is literature out there. And essentially, you need to start thinking of mechanism of how you're going to do data imputation, because then you're going to have a complete set, including the imputed values of monthly values, and then you can use the standard framework of vector autoregressive models, because then you have completed your data once you impose some imputation methods, which is going to be combined with your estimation method of the vector autoregressive model parameters. The other way that they do it is, remember how we did it in regression, where you take the 3 monthly variables in the quarter and you create 3 variables, one for December, one for the last month of the quarter, for the middle month, and for the first month. So essentially, you expand your variables, and therefore you create a data structure that is at the quarterly level, and you expand the number of variables. So essentially, which of course means that you also expand the parameter space. If you had 2 high-frequency variables at the monthly level, you're going to create 3 times Q variables, but that means that your transition matrices, they're going to be 3Q by 3Q, plus, of course, the P low-frequency variable, so they're going to be 3Q plus P times 3Q plus P. So again, you get into very large parameter spaces, and that's kind of a challenge. I'm not going to go into methodology. There are a number of interesting papers in the last 3-4 years of trying to use a number of ideas from high-frequency vector autoregressive models, which has been a topic of a lot of recent work, similar to high-dimensional regression. And I'm just going to show you some results focusing only on the GDP. So what we're going to show here is with respect, again, to the random walk model. So we're going to sort of, no, here I'm showing you directly. I'm not calibrating with respect to a benchmark model. So I'm showing you mean absolute error of the forecasting error. using data up to 2018 and going all the way to 2022. So here we include COVID, and therefore that's why the mean absolute error for all these models is not very, very good, because it includes the 2-3 quarters of the COVID shock. And I tried different type of methods. One is vector autoregressive models based on Midas type of technology, and they don't perform well at all. They are too inflexible. Surprising Bayesian VAR models, some work that we have done, introduces much more flexibility. We tried models based on feed-forward networks, and then some other flavors of recent neural network technology that utilize either sequence-to-sequence models or transformers. And you can see that maybe because of the inclusion of the COVID shock, these very flexible neural network multivariate models perform better, but definitely none of them performs extremely well. So on that point, I just wanted to take you on a small tour of the interesting things that and interesting challenges that mixed frequency data pose. I went into a little bit more depth on the regression framework because it's much easier to illustrate both the technical aspects and how you can develop these more flexible models. There is a lot of very interesting work on multivariate models because there is a lot of demand for them. People are not interested only in a single indicator. And I'll stop here. Thank you very much for your attention. And here are some of the references. The original paper where we developed the framework for mixed frequency is forthcoming in the Annals of Applied Statistics. The Bayesian vector autoregressive model, that's performing fairly well, is another paper which has other methodological challenges. And we also have tried some of the neural network that seem to outperform, especially when you include the COVID period. So if you're interested, take a look, or if there are any other interest in this work or to point out to good papers. A lot of the papers are, as I mentioned, the econometric literature because econometricians have been thinking about this problem for the last 15 years. I'll stop here. Thanks much, Sophia.